Okay, so in this module, I want to reintroduce some concepts that we learned back in Module 6, but this time focusing on some parts that were oversimplified in that module. So this is where we were talking about the standard error of the mean, and saying that for a population with a mean and a variance, if we take samples, in this case samples with n equals 50, each one of those samples is going to have a center denoted by x bar that is close to our population mean, but not exactly it, and a spread that is close to our population standard deviation, but not exactly it, right? And so I've shown down here 50 samples from a distribution that has a mean of 10 and a standard deviation of 5, and we see our mean is very close to our population mean, right? Our sample mean is close to our population mean, but it's not exactly there. The larger the sample size, the more likely the sample mean is to be close to the population mean. And the way that we can describe that phenomenon is by taking many different samples, each time recording their mean, and then it generates this distribution over here on the right, which is the sampling distribution, right? And so if we want to describe the spread of the sampling distribution, we have this formula where we have the population mean divided by the square root of n, right? And that's going to give us the population, is going to give us the standard deviation of the sampling distribution. And so this standard error of mean or sampling or standard deviation of the sampling distribution can be combined with the fact that the sampling distribution is a normal distribution. And a normal distribution has certain useful properties. We know the shape of it. We know that 95.5% of the probability density function in a normal distribution is going to fall within 2 standard deviations of the mean, right? And so that gives us these useful things for generating confidence intervals, right? So confidence interval here would be the mean, the population mean, plus or minus z times the population standard deviation divided by the square root of n, right? So z is a proxy for the number of standard deviations from the mean in a normal distribution. So z of 1 is 1 standard deviation above, z of negative 1, 1 standard deviation below. But what I didn't make explicit back then is that this version of the confidence interval, right, is telling you how close the sample means are to the population mean. All right, so we're starting out with our population mean and our population standard deviation, and we're seeing that the distribution of sample means around it is going to be in this normal curve, right? And we can describe the likelihood that the sample means are going to be close to the population mean using this equation, right? But this isn't quite as useful to us as this other version, right, where we describe how close the population mean is to the sample mean. And that's because in almost all cases that you are using this concept, you're going to be starting with a sample mean and a sample standard deviation and trying to backtrack to find your population mean and your population standard deviation. So we could do it in a similar way. We estimate our standard error of the mean using the sample standard deviation and our sample size, right? And then we have some information about the curve, and that's going to get us to a confidence interval. But the tricky bit here is that when you're looking at the distribution of potential population means around the sample mean, they don't form a normal curve the way the sample means formed around our population mean. Right, so when we're going backwards, it's not a normal curve. Right, and the reason it's not a normal curve is because we don't know the true value of the sample standard deviation. We don't know the true value, we don't know the true value of the population standard deviation. We don't know the true value of the population mean. Because we're estimating, there's some uncertainty involved. And that uncertainty is represented by the fact that we're now going to use the t distribution as opposed to using the z distribution. Z was normal, t is a new distribution. So what is a t distribution? The student t distribution is a fatter-tailed version of the normal distribution. And that is going to account for the uncertainty that's introduced by using the sample standard deviation and the sample mean. And so the t distribution has n-1 degrees of freedom, and just like with the sample variance, we're dividing by n-1. Now the t distribution has n-1 degrees of freedom, and as n goes to infinity, the t distribution just becomes a normal distribution. So in green here are a series of t distributions, and in blue is a normal distribution. And you could see for the degrees of freedom of only 2, it's a very fat-tailed curve with a low peak. But as the degrees of freedom increase and increase and increase, trending towards infinity, these tails get smaller, and it starts to match more and more just the normal distribution. So again, this accounts for the fact that we don't know the true population variance most of the time, and we're using the statistic S instead of the parameter sigma. So, okay, how do we end up finding these t distribution values? We're going to use it very similar to the way we use the normal distribution. It's just going to have slightly different values when we put it into our confidence interval. So in R, to get the t value for the confidence intervals, you use this function qt, and it has 2 inputs. It has range and degrees of freedom. So for example, if we wanted to get a 95% confidence interval, two-tailed with degrees of freedom equaling 10, we would input into the qt function 0.025, comma 0.975, and then comma, you could put df equals 10 or just 10, right? And then that's going to give you the t value, which is plus or minus 2.22. So minus 2.22 plus 2.22. And so if we did this with a degrees of freedom equaling 10,000 as it starts to approach the normal distribution, you would see what you would expect for a normal distribution, negative 1.96, and 1.96, you'll recognize those as the 95% confidence intervals for 95% confidence intervals for the normal distribution, right? So 95% of the normal distribution is going to fall within these two values. Conversely, for a t distribution, 95% of the probability distribution is going to fall between these two for degrees of freedom 10 and these two for degrees of freedom 10,000, right? So as the degrees of freedom gets very high, it just looks and acts much like our normal distribution. So if you're trying to get your 95% confidence interval, rather than using the normal distribution like we had in the past, now you would just find your confidence intervals using R and your qt function. You'd input the number of degrees of freedom based on your number of samples minus 1. And now you could take your sample mean plus or minus, in this case for degrees of freedom equal to 10, 2.22 times your variance, sample variance divided by square root of the number of samples, right? So this ultimately becomes your equation for 95% confidence interval, and unless you explicitly have the probability distribution or you're given the true variance of a population, you should always use this definition for your 95% confidence interval using this student's t distribution. And we'll be touching on the student's t distribution again when we talk about t-tests. But for now, we can leave it at that. This is your definition for 95% confidence interval, and this is why we use it.